that number is $13. On the downside, 20% below the mean, which is going to be negative 10%, so 9. So there's a chance that 16% chance it will be below $9, 16% chance that it will be above $13. Suddenly the volatility went up to, let's say, 25. Now that's one standard deviation number is 25. So there's still a 16% chance for the stock to be above 13.5. If you actually calculate it, the chances that it's going to be above 13, it's going to be more than 16. We could do it, but I'm not going to. So as volatility goes up, probability of an option finishing in the money is actually going up. In fact, delta is kind of another measure, the absolute value for the delta, for the option to finish in the money, for European options with no dividends. So roughly speaking, if stock returns are normally distributed, this option has 68% chance it's going to finish in the money. If I increase that volatility to 70, that delta is going to go up, or let's reduce it to 40. It didn't change by much, but it does change, all right? But it affects the value quite a bit. So at 40, it's 124. At 60, it's 150. And you can see that that affects at 60, put option is 47. At 40, 22. So both calls and puts are positively related to volatility. That means if you short this option, which means you sold it, value of that option goes up when volatility goes up, but since you short it, you're losing money. Because if you wanted to close that position, you would have had to close it at a higher price. So that's why we call that a Vega exposure. I haven't calculated that yet. All I'm going to do is I'm going to calculate the value when the volatility is up by 1 basis points. D8 was my volatility, plus 0 points. Come on. I can't see. Okay, there's a better way to see it. Let's make this bigger. I'm going to get that to original form, change the volatility argument by 0.01%. Okay. Basically, the volatility goes up by 1 basis point. If you want, you could do just 1% versus what it is now. So that's your Vega exposure. And I multiply that by 100. So the contract's value is going to change by that much. For shorter term options, Vega exposure typically is not that high, but let's make this into a long-term contract. Of course, there is no contract that expires on that day. Most option contracts expire on a Friday. So it's a little bit higher. But remember, this is only for 1 basis points increase in volatility. Typically, volatility increases are a lot bigger than that. So if you want to think 1% change, multiply that by 100. Remember, these are approximations. There is another exposure we have, It's called delta decay. I think this is called charm. Let me check. So I have enough time to calculate the minor Greeks. Like the major Greeks are the Leonidas, Pericles, and the minor Greeks is the marathon guy. That wasn't the one. Where did I find that the other day? Um, I don't use Wikipedia for many things, but sometimes I get them relatively quickly. Okay, charm is delta decay. In addition to not being the same, when the price moves, delta also changes over time. You can think of charm as the theta for delta. So if nothing happens, but just one day passes, my delta is going to change. So the way I'm going to do it, uh, I'm going to take my gamma formula. Let's call this charm or delta decay. Instead of changing the price, I'm going to make the time one day less. Time was B7, just like we did in theta. Okay. That's how much delta would change. But this is a very long-term option. Typically, both theta and charm would be small. How about this one? Now you have a pretty big change, relatively speaking, in delta. So currently, this is a put. Let's make it a call. If you sold this call option, you would have to buy to be delta neutral 76.33 shares. And nothing happens in the market except time passes. Tomorrow, that decays, that delta is going to be lower, and you would have to basically sell some of it. So we need to worry about those too. But that's if you're running a really big option book, you worry about those. And there is one more thing I'm going to do. It's called lambda, or essentially the leverage. That's where the L comes from. Lambda is the equivalent of the letter L in the Greek alphabet. It basically says, what is the implied leverage? For example, if I increase the spot price, let me make this a long-term option. Okay. At this current price, this option is worth $4.46. Let's increase the spot price by 10%. Okay. So that means price is going to go to 26.40. And if there is no leverage, that price should go up by only 10%, which is going to be about 45 cents. So it should be about $5. But if there is leverage, it's going to be much higher. It's actually much higher. So there is an implied leverage. It actually went up by about 30%, roughly speaking. So you had underlying went up by 10, your position went up by 30. That means you're effectively 3 times leveraged. It's as if You put in $100, you borrow $200 more, and you bought $300 worth of shares. And that's what lambda is. It gives you the measure of leverage. Let me see what it is. Lambda. No, that's gamma. Okay, it's delta times underlying price divided by the value of the option. We actually have everything in there. Let's just put that in, and delta times uh, underlying price, where are you? Divided by value of the option. I kind of eyeballed it and I said about 3 times. The exact number is 318. And the more out of the money, the more leverage there is. For example, let's say the strike is, let's go back to 24. That was the original one. Let's say strike was 40. Look at the implied leverage on that one, 5. The trouble with way out of the money options, especially if the term is small, you're subject to a lot of theta decay. Okay. But if you got 3 years, you could withstand some theta. If you make money, you're going to make it 5 times the speed of the actual stock market change. Let's stop here. On Monday, we're going to actually use all of these and figure out how to make an option book, delta, gamma, theta, vega, and possibly charm neutral. All right? But at a minimum, delta, gamma neutral.